Hello everyone, welcome to our discussion of section 3.2 where we will be talking about inverse functions and limits of logarithmic functions. Both of these topics you're already familiar with from previous classes such as the college algebra, which was Math 124, or Pre-Calculus 1, which was Math 126. So in this section we will just do a quick review of those concepts and add just a little bit to it. By that I mean we just add, for example, taking the limits of logarithmic functions, such things like that. But pretty much I'd say at least 80% of this section it would be all review for you. So you recall from college algebra and pre-calculus that if we have a function, the relationship between a function and its inverse is such that the domain of the original function becomes the range of the inverse function, and the range of the original function becomes the domain of the inverse function, and vice versa, of course. So the range of the inverse function is the domain of the original function, and like that. So we already know that a connection between a function and its inverse. So let's just solidify that concept with a quick, easy example. Suppose if we know that if we have f of or the value of the function at 6 is equal to 17, and function f, is supposed to be a one-to-one function. Again, recall from the previous courses that for a function to have an inverse, it must be a one-to-one function. So we're assuming that this function f satisfies that condition. And then we want to know the value of this, the value of the inverse function at 17. That's what we want to know. So just looking at this diagram, you can quickly remember what the answer to this question is, right? If the domain of the original function is the range of the inverse function, and the range of the original function is the domain of the inverse function, then we can quickly see that the answer for that is simply 6. Right? So if the value of function at 6 is 17, then the value of the inverse function at 17 is 6. So the domain became the range, or I should say not the domain, but a member of the domain became a member of the range, and a member of the range became a member of the domain. So having said that, again, I just create these bulleted lists as a recall to what we already know. So let's remember that not every function has an inverse. And that only one-to-one functions have an inverse. I should add, however, because I'm sure you've taken trigonometry, Math 127, so you remember that even though the trigonometric functions were not one-to-one, but on many occasions, we looked at their inverse value, or inverse trigonometric functions and their values at particular points along the domain. So how were we able to talk about that in Math 127 if trigonometric functions are not one-to-one? So recall that in those situations, we restricted the domain to a region where over that interval, the trigonometric function was in fact one-to-one. So we had to restrict the domain for them. And so let me mention that only one-to-one functions or functions with restricted domain and I'll give an example of that. With restricted domain to behave as a one-to-one function. Such as cosine of x, which of course is not one-to-one, but when we restrict the domain to x between 0 and pi, it in fact becomes a one-to-one function, such as cosine of x restricted to this interval, 0, x varying between 0 and pi. Okay, so only those kinds of functions can have an inverse. So let's do an example of that. So suppose, let's see. So here are some basic examples. So one is f of x equals 2x plus 5. F of x equals x. These are examples of one-to-one functions. And f of x equals x squared. Notice that f of x equals x squared is not a one-to-one function. But we can find the inverse for it if we restrict the function, this function, to some domain where it is a one-to-one function. So x varying between x greater than or equal to 0. So this x is restricted to this region, all positive values and 0. And in that case, it becomes a one-to-one function. And we can talk about the inverse of it then. Okay, the other thing that we should remember from previous courses is the horizontal line test. Remember that? So horizontal line test is a test where if we draw a horizontal line through the graph of some expression, if this horizontal line intersects the graph at any point only once, then the function that generates that graph is a one-to-one function. But if the horizontal line intersects the graph at more than one point, then the function is not one-to-one. So this is from the past. My ink is drying on that one, so only if and only if so no horizontal line intersects its graph more than once, like that. So what are some examples of this? Let's draw a few of these. So we can have, let me draw 3 such examples. 1, 2, and 3. So this is our x-axis, and of course the y-axis. Oops. One here, and here, and one here, like that. Okay, so we have, suppose if we have a graph like this, I'm sure you'll recognize this graph very quickly, that one, right? Remember what this represents, which function? It's the cubic function, right? So suppose if we have f of x equals x cubed, and of course you can see that a horizontal line, any horizontal line, will intersect this graph at only one point, right? If we draw it here or if we draw it here, it's the same story. So this is in fact a one-to-one function. Okay, so let's take the basic quadratic function, which has a graph like this. Right, x squared. So of course this is, at this point, this is not a one-to-one function, right? A horizontal line we can draw, we can find a horizontal line that intersects that graph at more than one point. So this is not a one-to-one function. Now guess what? So I'm going to change this slightly. So I'm going to say the graph of the basic quadratic function, or f of x equals x squared, but this time I'm going to restrict the domain for this to just x greater than or equal to 0. So what will that do to this graph? Can you see it already before I draw it? So if the domain is restricted from 0 to infinity, so we're going to have just this piece, right? So it's going to be that piece only. So now, if you draw, once you restrict the domain, you can draw a horizontal line anywhere, and it will intersect the graph at only one point. So now we have a one-to-one function. Okay, so that's what we mean by restricting the domain to create a one-to-one function out of a function that originally is not a one-to-one function. So the other thing that we should remember about inverse function is what kind of interpretation do their graphs have? Do you remember that? Do you remember how the graph of a function is related to the graph of its inverse? Do you remember that? Let me get rid of the shadow there from the, I wanted to turn the light off that hits directly above this projector. Hopefully that'll create a better resolution image on the screen. Okay, so let's talk about that. The graphical interpretation of a function and the graph of its inverse. So its inverse. So let me just begin with a graph first, and then I'll put the description for it right afterwards. But suppose we have such a graph. So we have the x and y axis as usual, right? Do you know where the line y equal x is located within this set of axes? Do you know where it would be? The line y equals x. That is a line where the x and y coordinates of any point on that line are equal to each other. So 2, 2, 3, 3, -1, -1, 5, 5, 6, -6, -6. So on such a line is called y equals x, and it goes right through the origin, dissecting the first and the third quadrants. So let me draw it as a dashed line. So this is the line y equals x. Okay? The y and x coordinates of any point on this line are equal to each other. Y equals x. So if we have a function that graphs like this, it graphs such as like this, let's say, let's just assume something like that. And let's call this f of x. I don't know if this is, let's see, some function, right? Because I'm not sure if I have the correct function on the paper. But let's say some function graphs like that. Then the inverse, and we assume this is some one-to-one function, right? Let's assume that. Now, the inverse of this function would be, graphically speaking, would be mirror image of this line across the y equals x line. Okay, so that would be, let me use a different color to draw that, and that would be so if this is like that, so that would be something like this. If I can draw it like that. Like that. Okay. So if that's f of x, then this would be f inverse of x. So this is always the relationship graphical relationship between a function and its inverse. The two are mirror images of each other across the y equals x line. And I better just make this a little bit darker because it looked like it doesn't show very well like that. So now it stands out. Okay, so that's basically the graphical representation. Now let's write this down. So graphically, reflecting the graph of a one-to-one function across the line y equals x. Again, this is the line where that represents that dashed line is meant to represent that, and that's all the x and y coordinates on this line are equal to each other. will obtain the graph of the inverse function. Okay, so that's basically the graphical connection between those two. So how do we know if somebody comes and claims that two functions are inverses of each other? How do we prove or disprove that claim? So that's the next topic for us. So method to prove if and when two functions are inverses of each other. It's very easy, and this is again a review topic. I'm sure you've seen this before in one of the previous prerequisite courses. So we say if the composition of a function and its inverse and its function and its inverse equals x, and this is very important, and so that's not a sufficient condition. If the composition of a function and its inverse equals x and vice versa, in other words, the composition of the inverse of a function and a function equals x, if this is true in both cases, then the two functions are in fact inverses of each other. Okay, so this is saying that in plain English, but how do we show this symbolically? Let's use mathematical symbols to say the same thing. So let's say, in other words, this is what we have. The composition of a function and its inverse should equal x, and so that's not sufficient. And the same thing, vice versa, should be equal to x as well. So the composition of the inverse function and the original function should also be equal to x. So these two should be true at the same time. Individually, they're not sufficient, but together they are sufficient proof that two functions are inverses of each other. So now that we've discussed this, how do we find the inverse of a function, of a one-to-one function, of course, right? The function has to be one-to-one, one-to-one. So steps Okay, so this is very similar to the steps you would have seen in one of the previous prerequisite courses, but it might be a little bit different. The author is different, so it might be different than what you, but it's pretty much the same technique. It's just verbalized or organized in a different way. But I'm sure you've seen this method in the past. But I like to explain it the way your book explains it because there are advantages to this way of looking at it. It's just a different way of stating the same set of procedure. That's all. So step one, we want to replace f of x notation with y. That's the first step. Of course, if you have the y, then you skip this one. Second step, solve for x or whatever the independent variable happens to be. I'm just saying x, but it could be t, any other letter. But you solve for the independent variable. And then finally, once you're done with step 2, replace x with f inverse of x notation and y with x. So you replace, once you solve for x, you replace x with this notation, the inverse function notation, and you replace y in that final result with x. Okay, so let's do one example. It shouldn't be too difficult to follow all this because these are review. I'm sure you recognize that these are all review topics. So let's find the inverse of this function. So inverse of f of x equals x to the 4 power plus 1. I'm sure some of you, if not all of you, right away you notice that this is not a one-to-one function. So is this a quick trick question to find the inverse of a function that is not one-to-one? No, it's not a trick question, because what I'm about to do is to restrict this domain. So I'm going to restrict the domain to x being greater than or equal to 0. So now it is a one-to-one function, of course. Okay, so the solution of this. So what did we say in that procedure? We said replace f of x with y. Let's do that. And then solve for x. So we're going to replace f of x with y. Y equals x to the 4th plus 1. And then we have to solve for x. Let's do that. So we have x to the 4 equals y minus 1. So basically, I kept x to the 4 on the same side and moved this plus 1 to the other side. That's what I'm doing. But I put that on the left because it's just a habit for me to put the variable for which I'm solving on the left side. That's all. So now, to solve for x, all we have to do is take the 4th root of both sides. Let's do that. Like that. Is this correct? What do you think? Is this correct? No, it's not, right? Because this is I'm taking the even root of these two sides, and we know that because this is an even root, then we must have plus or minus, not just positive, but plus or minus this quantity. So this is something that we need to remember that we have. But are both of these answers correct? Because what do we have on the left? On the left we have I need to also put this 4 here. So we're taking the 4th root of, maybe I should put red ink on it. We're taking the fourth root of both sides because this power, we're solving for x and x has power 4. So if it had power 5, we would be taking the fifth root of both sides. It has power 4. So fourth root of both sides. And it's an even root. So we have to have plus or minus. Of fourth root of y minus 1. But can we accept both of these solutions? Can we? No, we cannot. Why? Why not? Well, we had a condition that says that the x must be either equal to 0 or greater than 0. That was part of the condition of making this function a one-to-one function. So we cannot accept the negative one, right? X has to be positive. So we cannot accept the negative. We only can accept the positive version. Therefore, x equals fourth root of y minus 1, right? And let me quickly add, because x should be greater than or equal to 0 according to this condition we had at the start. Oh, one thing so I should actually finish this. What I boxed is not the final answer. So what do I need to do? I need to replace x with this notation, the inverse function notation, and y with x. Sorry about that. Sorry to disappoint you, but that's not the final answer. The final answer is f inverse of x is equal to fourth root of x minus 1. Now that is the final answer. Okay. All right. So let's see if we have, what else do we have here on this page? So there's a theorem, your book talks about it, and I suppose sometimes it could be useful. Let's talk about it. And we'll do examples here in the lecture as well as on the worksheets during your discussion session and in class. Okay, so this is a theorem. So the theorem says that if f is a one-to-one function that is continuous, over some interval, right? Then its inverse function is also continuous on that interval. Okay, so this is a natural extension of two functions being inverses of each other. If one is continuous over some interval, then the inverse is also continuous over that same interval. Another theorem. This is just a formula, so I'm just going to go ahead and write it down. It says that, let me write it down, then I'll explain what it's saying. So this is saying that if you want to find the derivative of the inverse of a function at some point, you can calculate it as, this is another way of calculating it. Of course, you can find the inverse function, then you can take the derivative of that inverse function, and then evaluate it at a. That would be one obvious way of calculating it. But another way of calculating it is take the reciprocal, find the derivative of the original function, then evaluate that derivative, take the composition of that derivative function with the inverse function, and evaluate that whole composition of functions at a. Okay, so find the inverse. So this is a relationship between the derivative of an inverse function and the derivative of the original function and the inverse function. It just establishes a connection between these different entities. In that way, it's an interesting formula. Not that, so the purpose of this, as you look at this, don't look at it as, why is it making things more difficult? That's not the intention of this formula, to make things easier. No. The intention of this is to show you the connection between the derivative of the inverse of a function and the derivative of your original function and the inverse function itself. So it establishes a connection between these different entities. That's the value of this formula. Okay, and we'll do examples of applying this formula. As a matter of fact, here comes an example right away. So let me move to the next page. So in mathematics, quite often we are looking for relationships or patterns of connection between different entities. Okay, so here in this example, we want to find. So suppose if we have a function like this, if f of x is equal to x cubed plus 3 sine of x plus 2 cosine of x, if that's the function we have, we want to find this quantity. Derivative of the inverse function evaluated at 2. Okay? That's what we want to do. So if we bring back that formula, so this is derivative of the inverse function, right? So the derivative of the inverse function at some a, in this case, in this example is 2, would be equal to that. Let me just adapt this formula for our particular example. So we have f inverse, derivative of f inverse at 2 would be equal to 1 divided by derivative of derivative of f at 2. Okay, so that's the formula we have. To answer that, we can apply this formula, or we can use this relationship between these different entities. Okay, well, one of the things we know, well, let me see, I think, so also knowing one piece of information I forgot to add, let me add that here at the end. If that's the function, and we know that f function value at 0 is equal to 2, right? Let's assume that. I mean, we can plug in and also figure that out very quickly. Then find this quantity. Well, we know that if f of 0, so because that's given, because and also we can calculate it. Because of that, therefore, And remember that first thing we talked about? Remember this example? Let me bring it back. That f of the connection between a function and its inverse is that the domain is equal to the range, and the range is equal to the domain. So, and the example we gave was this. If function at 6 is equals 17, then the inverse function at 17 equals 6. Right? So now, because we know if the function value at 0 is equal to 2, then we can say that f inverse at 2 equals 0. Okay? Do you see the connection now? So that we already know that that function is equal, that whole thing inside the parentheses is equal to 0. Now all we need to do is evaluate, find the derivative, and then evaluate the derivative of f at 0, because we know that piece is 0. So let's find the derivative. And also, so because of this, and also that the derivative of that original function is equal to 3x squared plus 3 cosine of x minus 2 sine of x, right? This is the derivative of that. So now let's evaluate this at 0, because this is the derivative. And we know this quantity is equal to 0. So let's evaluate that, because that would give us the answer to what we're looking for. So given that and all of this, we can write the inverse, the derivative of the inverse function at 2 would be equal to 1 over this derivative evaluated at 0. Because this is what we're doing. This is what we're doing. Okay, that is equal to 0. We figured that out because of this connection. So we say then would be equal to 1 over that derivative evaluated at 0. 3 times 0 squared plus 3 times cosine 0 minus 2 sine 0. Okay? So then let's calculate that. It's equal to 1 over, this is 0. Cosine of 0 is, well, that drops out to 0, plus cosine of 0, do you remember from trigonometry, that is equal to 1. So 3 times 1. So we have 0 plus 3. And sine of 0 is 0 times 2 times minus 2. That will be minus 0. So ultimately, the final answer for this would be 1/3. Okay, so that's that. So that's just an application of that formula. Quite frankly, I haven't seen many applications of this formula, but your book talks about it, and I wanted to talk about it. So you have now, we've talked about it, and you've seen an example of it. We'll do more examples, by the way, on the worksheets that we'll do in class or during the discussion sessions. Okay, so after this, we come to the logarithmic functions and their limits. This is, I'm sure, again, is a review of all the stuff that you've seen in previous courses. Going all the way back to the high school, right? You've seen log functions in high school, I'm sure. So logarithmic functions and their limits. This is pretty straightforward and simple procedure, and it makes a lot of sense in the context of what you've already learned about calculating limits. So it's going to be pretty straightforward, everything. Okay, so let's talk about some of the properties of log functions that we've learned in the previous prerequisite classes. So recall from Math 124 or Math 126 that so we have log of, let's take this to some base a. To some base a of x equals y. If this is what we have, then this is equivalent to its exponential function version, right? This is the log function. Its exponential function version would be a, this base, to this exponent equals x. Okay, remember that log functions are the only function that generate an exponent. So this, whatever you have on the other side, is an exponent. To what base? To this base. So this base raised to that exponent gives you this result. Okay, and so this is the log form, this is the exponential function form. Another property of log functions that we learned was log to base a. Oh, by the way, so this a could be negative or positive, but for a greater than, those are that are greater than, I meant to say that it could be less than 1 or greater than 1, but the ones that are, the bases that are greater than 1 are far more important than the ones that are less than 1. So we mainly consider those log functions with base greater than 1. Okay, just remember that. So so let me actually write that in this corner, that the most important log functions have a greater than 1, and we want to highlight that and remember that. Okay, so these a's can be anything greater than 1. Okay, so then we have a to the x. Log of this entity to a base equal to that is simply equals x, and so we assume that x belongs to all real numbers. Okay, and then this is a little useful property here. If you have some value, positive value greater than 1, raised to a log of a function to base a, so compare this with that. If that is the case, so 2, let's say 2 to log to base 2 of x, that would be equal to x, right? Equal to simply that. For any x, this is true for any x greater than 0. Okay. And let's talk about this property, log of x times y. So x and y are being multiplied by each other, and this base is some base a. Then that is equal to, so the product problem or the multiplication problem can be converted to an addition problem. Log of x to base a plus log of y to base a. I hope this is just refreshing your memory about these properties that you've seen before. Okay, so the quotient, the log of a quotient becomes the log of the difference between those two, or the difference between the logs. So log of this quotient x over y to some base a would be equal to log of a to base a minus log of y to base a. Like that. And then, of course, not last, but somewhere in the middle, but this is a very important property. So log of x to the r to base a, here we can simply bring this r down and in front. We can use this technique a lot when we solve for the variable that is in the exponent. So log of x to base a. And this r can be anything, any real number. Okay, so we can actually mention that here. Okay, so what else? So let's add a few properties to this. If the base, as we mentioned, is greater than 1, then this is what we can say. We can say this is now bringing back the limits. Then limit of log of x to base a as, let's say, the x approaching infinity would be equal to infinity, and limit of log of x to base a as x approaches 0 from the right would be equal to minus infinity. Okay, so like that. Because of course we cannot approach 0 from the left, right? You remember that the log of a negative number is not defined. So we have to approach 0 from the right, where values are positive. And when we do that, the closer we get to 0 from the right-hand side, from the positive side of the real number line, we can calculate smaller and a smaller and a smaller negative values. Okay, and this is of course the opposite. The larger this value, the log of it will also be large values. Okay, so we have more properties of log functions coming up. And so if we have log to base e, right? Remember that number we talked about last time? Log of any entity to base e is equivalent to the natural log of x. So if you see natural log, you're really seeing log to base e. Okay? And so natural log of x equals y. We can write this in the form of its equivalent exponential function, which would be, this is the exponent, right? Log and natural log functions generate an exponent, so this y is an exponent to what base? Well, the base e, right? So e to that exponent equals this result. Like that. And of course, natural log of e to the x would be equal to x here, x. And of course, where x has to be greater than 0. Okay. So then, what else? So let's also this property, this neat property. Do you remember this from the past, from previous classes? E to natural log of x is equal to x. And let's see. So that, well, this actually, this belongs here. So let me not include that there. It's just where x is greater than 0. Like that. And then a few other ones that are very, very useful actually. Natural log of e is equal to 1. Log of 1 is equal to 0, as well as natural log of 1 equals to 0. Also change of base formula. So we have, so log of x to base a, and then natural log, that's equal to natural log of x divided by natural log of a, also equals log of x over log of a. And of course a, so a is not equal to 1 because we would get 0, right? And we don't want 0 in the denominator. A couple of more properties, and we'll do some examples. So limit of natural log of x as x2 goes to infinity. You already know the answer, right? It's so straightforward to see. So the larger and larger the x value gets, what happens to the natural log of x? It becomes larger and larger too. So that's equal to infinity. And so limit of x as it approaches, or limit of the natural log of x as x approaches 0 from the positive side, it would be equal to minus infinity, because the natural log or log of any value between 0 and 1 is a negative number, right? This is what we know this from the previous courses. So I want to go back and just highlight, because we introduced a whole bunch of stuff, or we talked about a whole bunch of stuff that are review, but we introduced a couple of ones that are new, right? Especially these ones that involve limits. So I want to highlight these. So these are brand new stuff, applying the limit, and also these two were brand new. Okay, like that. But they make sense. Okay, so let us then do some examples. We'll do one more example here. One, maybe more. I think at least one. We'll do two, actually. So let's do a couple of examples of finding the inverse of a function. So find the inverse of this function. F of x equals 4x minus 1 divided by 2x plus 3. Okay, so we did mention the procedure for this. Let me just bring that back for a second. So there it is. Remember this? This is on page 2. That steps to finding the inverse of a one-to-one function are as follows. Replace f of x with y. Let's do that right away. So this is our solution. In fact, why don't you pause the video and find the inverse of this and then unpause the video to see my solution. That would be very good if you did that. And so I'm going to do that. I'm going to replace that f of x with y. Then what was the next step? Do you remember? It said we have to solve for x. So let's solve for x. So let's multiply both sides by 2x plus 3. That's just to get rid of the fraction form, right? We don't like fraction form. And then so on this side, we have the 2 cancel each other out. On the left, we have 2xy plus 3 times y equals 4x minus 1. So we're still solving for x, right? Let's continue until we're done with that step. So we have 2xy minus 4x equals anything that doesn't have x in it, move it to the other side, minus 1 minus 3y. Then x appears in 2 terms, but we're solving for it, so we need to isolate it in order to solve for it. So let's factor it out. 2y minus 4 equals minus 1 minus 3y. And then solving for x, we need to divide both sides by 2y minus 4. So minus 1 minus 3y divided by 2y minus 4. And of course, we can factor out the negative from the numerator and multiply the denominator by it. And let me do that here. So we have x equals minus 1 plus 3y divided by 2y minus 4. Now let me multiply the denominator by that minus. So we have x equals 1 plus 3y divided by 4 minus 2y. And then the last step, right, which was replace x, because we've solved for x now. Replace x with the inverse function notation and y with x. So let's do that. And so f inverse of x is equal to 1 plus 3x divided by 4 minus 2x. And that's the inverse function. So let's do another one, just to refresh our memory, right, about this stuff. So we have, we want to find the inverse of this function, y equals natural log of x plus 3. So solution of that. So this is already y. We don't have to switch from f of x to y. But here's, because of this natural log, see, this we need to, as you saw here, we need to solve for x. We need to, next step is to solve for x. But x is now caught up in this group, in this parentheses group, and as part of natural log. So it's natural log of this. In order to solve for x, we have no choice but to get this x out of this group and out of this argument of natural log function. We need to do that. How can we do that? So recall, this is from one of the properties that we just mentioned. Recall that e to natural log of x equals x, right? It should be one. I remember it's one of the ones that we mentioned. Let me see if I. So it's that one. We're using that one. E to natural log of x equals x. Recall that. Now raise both of these sides to base e. Okay, we're going to use that because, why are we doing this? Because once you do that, you're going to see this operation gets rid of the natural log. You end up with the argument by itself. And that's what we want, because then we can isolate x. So let's do that. So e to y on the left, and then also e to that whole thing. Natural log of x plus 3, right? So on the left, we're okay. It's just e to y. On the right, this is we're going to be left just with the argument of the natural log function, because that is the exponent of e. So we have x plus 3. Okay? And remember, we're solving for x, right? So then x would be equal to e to the y minus 3. So we've solved for x now, but the last step is, what do we have to do? Do you remember? We need to change this to f inverse. So f inverse of x equals, and replace y with x, e to the x minus 3. And this is what the final inverse function looks like. Okay, like that. Okay, so let's do more examples of different kind. So in this example, or series of examples, actually there's more than one. Let's see. We have a couple of these. And what we want to do is, without a calculator, find the exact value of each function. So we have a, and that is, this function, natural log of 1 over e. So we want to evaluate this without a calculator. Well, we already know that this, we can rewrite this in terms of negative power. So natural log of e to minus 1 power, right? This is just that rewritten in a different form. And we know that this, we can apply one of those properties. Let's bring them back. Let's take a look at those. One of the ones that put the exponential or exponent in front, we can apply this one, that one, right? The r, the exponent comes in front, multiplies by the whole thing. Let's do that. So then we have minus 1 times natural log of e, right? But we know natural log of e is 1, right? We know that that is equal to 1. So minus 1 times 1 is equal to minus 1. Like that. Okay, so that was an easy one. Let's do another one. So this time we want to find the value of this log of 100 to base 3 minus log of 18 to base 3 minus log of 50 to base 3. And we're asking, what is that, without the use of a calculator? Well, remember that in order for us to apply the log properties that we just mentioned a few minutes ago, the bases have to be equal, right? And certainly in this case, they're equal. So because of that, now we can apply the properties. So let's say this difference, we can change that to a quotient. So log to base 3 of 100 divided by 18 minus log to base 3 of 50. Okay. Now this is another difference. So we can take yet another ratio of this divided by 50. Okay, let's do that. Actually, I should have switched. I meant to switch to a different color, but I forgot. Like that. Sorry about that. Like that. Okay, so then log to base 3 of 100 divided by 18 divided by 50, and we want to know what that is without a calculator. Now this is a complex fraction. Let's simplify it. Log to base 3 of 100 divided by 900, that's 50 times 18, equals question mark. Of course we can simplify this, right? Log to base 3 of 1 over 9 equals question mark. So let's replace this question mark. It's a value we're looking for, right? So what if I replace it with x? Because x is what we're looking for, that value. So log of 1 over 9 to base 3, let's say equals x, right? So now let's write the equivalent form of this in exponential form, or equivalent exponential form of this. Let's write that down. That's easily done because we know that's an exponent. Log function and natural log functions generate an exponent. So we have this base to that exponent, 3 to the x equals 1 over 9, right? So now let's rewrite the right-hand side in power form. So 3 to the x equals 9 to minus 1 power. Also, we can rewrite 9 as 3 squared, right? So 3 to the x equals 3 squared to minus 1 power. And by the properties of exponents, we know this can multiply that by that. So we have 3 to the x equals 3 to minus 2. So you see right away that if the two sides are to be equal to each other, then this value that we were looking for, which we labeled as x, must be equal to negative 2. So x must be equal to that. Okay, that. So let's use those properties that we mentioned to expand a logarithmic or natural logarithmic expression. Because you know from the past that we can use those properties either to expand a logarithmic or natural logarithmic expression or to contract and combine them or make them smaller. Okay? So in this case, using the properties of logarithms, we want to expand this expression, natural log of s to the 4th power times square root of t times square root of u. Okay, so the first thing we can do is that we can change the multiplication problem to an addition problem, right? We had something like that. The multiplication problem can be changed to an addition problem, right? Let's do that. So we say natural log of s to the 4 plus natural log of all of this, like that. So let's rewrite these with rational exponents, or in that form. So we have, by the way, meanwhile, we can use those properties to bring this 4 to the front, right, and down. So 4 times natural log of s plus natural log of t, right? So we have a square root over the whole thing and a square root over u. So t times u to 1/2 power, that's that. And then put a parenthesis over the whole thing and raise that to 1/2 power. Okay? Now, the same thing we did with this 4, which bring it down and in front, we can do it with 1/2 and put it in front. So 4 times natural log of s plus 1/2 times natural log of t times u to 1/2. Okay, so all we did was put that in front. Okay, so now what we have is t multiplied by u to 1/2 power, right? So we can convert this to another addition of 2 terms. So we're expanding, right? So that's the idea. So 4 times natural log of s plus this 1/2 is going to be multiplied by everything that comes after it. So I'm going to put a bracket just to remind myself of that. Then we have natural log of t plus natural log of u to 1/2 power. So we expanded this product into addition of 2 terms. Now we can bring this down and in front, and we can distribute this 1/2 to both terms. That will be the full expansion of that original expression. So we have 4 times natural log of s plus 1/2 times natural log of t, right, plus 1/2 times this 1/2 brought in front, 1/2 of natural log of u. I just did it like this so you can see every step. But you don't have to do this on an exam. You can go as fast as you like. And if you can see from here to here, you can certainly jump from here to here, okay, to save time. So 4 natural log of s plus 1/2 natural log of t plus 1/4 natural log of u. Can we expand this any more than what we've done? No, right? This is the full expansion of the original expression. So let me box my final answer like that. So let's do the opposite of this. Here we expanded. Let's go the other way around and take a function, logarithmic function that is in expanded form, and contract it into as a small and as compact of an expression as we can. So we want to write the following as a single expression. Okay, so here's the expression we have. Natural log of a plus b plus natural log of a minus b minus 2 times natural log of c So what do we have here? We have addition, right? So we can go the opposite and multiply those two entities. So we can write natural log of, and this is a plus b times a minus b, so we have a squared minus b squared. Remember that shortcut formula we had, or we looked at, or we used back in Math 124 and Math 126? It's useful even now. And then minus 2 times natural log of c. Now we have a subtraction operation between these two natural log terms, so we can change this into a quotient, right? But even before that, what can we do with this 2? What can we do with that? Going back and writing this in more compact form, we can certainly put this back in a power, because that's where it can go. It can, if it's a power, we can put it in front. If it's in front, we can put it as a power. So let's do that. So natural log of a squared minus b squared minus natural log of c squared. Now, because we have a subtraction operation in between, we can write this in the form of a quotient. So natural log of a squared minus b squared over c squared. Okay, so can we make this any more compact than we've already done? We've already done? No, this is as compact of an expression as we can get. So that's where we stop. Okay, so let's see. Let's do more examples of different kind. So here we want to find, so what are the domain, range, and x-intercept of the function of the following function. Okay, so here's the function. F of x equals natural log of x minus 1 minus 1. And also, they want us to sketch the graph. So let me, so also sketch the graph. We want to do that too. Okay, like that. Okay, so first the domain, we know that the argument of a natural log or log function cannot be 0 or something negative, right? So this thing should be always something positive, a non-zero positive value. So x minus 1 must be greater than 0, right? Therefore, x must be greater than 1. So the domain would be parenthesis 1 comma infinity. The range, however, is there any restrictions on the range? Well, if we have some value that is between 0 and, well, it can be negative, right? If this value is small enough, we can have a negative value for f of x. So domain can be negative value. It could be positive value. If this is a very large value, then we have a very large quantity from all of this calculation. So it can either go towards negative infinity or positive infinity. So range, there's no restriction on range. The domain we have restriction, but the range, it's just from negative infinity to infinity. There's no restriction there. Then we're asked to find the x-intercept. Well, let's find that. The x-intercept happens when the y value is equal to 0 and we look for the x value, right? That's where the x-intercept would be. So let's substitute for f of x with 0 and find the x value here. So we have 0 equals natural log of x minus 1 minus 1. And so then we have natural log of x minus 1 equals 1. Now that's interesting, right? So we're solving for x. And so we can't solve for x unless it's out of this situation where it's part of the argument of a natural log function. So what technique we just used a few minutes ago to release this x from this group format? We just raise the whole thing to base e. So e to natural log of x minus 1 equals e to 1. So we do that to both sides, right? We're allowed to do that. So on the left, things become significantly simpler because this simplifies to x minus 1, and that side is just e. So then x, or x-intercept, is equal to 1 plus e. So x-intercept would be 1 plus e, comma 0. That's our x-intercept. Okay? And then we were also asked to graph this. So let's do that as best as we can without the use of a technology. So we have that. And this is the x-axis. And then we have the y-axis. And then, so let's see. So let's go back to the original function. See, we already know that this can't be, the x cannot be equal to 1, right? It should be greater than 1. So what happens at 1? At 1, when x equals 1, this becomes 0, and natural log of 0 is undefined. So at that point where x equals 1, we have a vertical asymptote. As a matter of fact, since right where we said that, let me also add that at x equals 1, we have a vertical asymptote. Okay, like that. So let's draw that here. So this would be x equals 1. All right. And if we were to find this x-intercept, it would be, so e, it's 2.71828 something, right? 2.718. So 1 plus that would be 3.718. So it would be somewhere near 4, but to the left of it. So if this is 1, this is 2, 3, and 4, right? So that intercept, that x-intercept, would be somewhere here. So let's call it 1 plus e, comma 0. that one. Okay, so that would be the x-intercept. And this is an exponential function, so so the graph, maybe I should, it would go off the page here, so let me extend this. So a graph of this would look like something, I'll try to draw this as best as I can, but it would be an increasing function going that way. It would be like that. Like that and like that. So this is increasing. Okay, like that. And let me write f of x equals natural log of x minus 1 minus 1. Okay, so that's what we have. A quick graph of that. So let's do a few solving problems, because solving is pretty important, applying these properties that we've been talking about. Again, we've done quite a lot of these in the previous prerequisite classes, but this would be just to refresh our mind about it. So solve the following. Let's say for part A, we want to solve natural log of x squared minus 1 equals to 3. So solving is about isolating the variable, right? And we can't isolate this variable unless it's free from this parentheses argument of the natural log function. Just like a couple of times we've done this so far in this video lesson. So we want to raise both sides to base e. So e to natural log of x squared minus 1 equals e cubed, right? Now we can apply that property that we have, that e raised to natural log of something is equal to that something without the natural log in front. So on the left, things simplify significantly. We have that. And then all of that equals e cubed. Now, of course, that, so all of this, then let me use up this blank space here. So x squared would be equal to e cubed plus 1, right? Just moving the negative 1 to the other side. And of course, we have x equals plus or minus square root of e cubed plus 1. Okay, like that. So let's see. So x equals that. Okay, so that would be, but of course, so this is because by the square root property, which again we learned about back in college algebra and pre-calculus, by square root property we get plus or minus, taking the square root of both sides we get plus or minus. But if you plug in the, let's see, if we plug in the positive, are both of them acceptable? Both of them are acceptable. The reason being, of course, that this is x squared, so it cancels the negative. So both answers are actually acceptable. So we accept both, like that. Because this power x squared will make this negative positive again. So that's why both answers are acceptable. Okay, so for part B, we have e to 2x power minus 3 times e to the x plus 2 equals 0. So whenever you see e to the x and then e to the 2x, it hints at we might be able to write this expression as a quadratic equation or factor it in some way. Let's see. So let's take, okay, so let's do it this way. So let u to be e to the x. Okay, now let's rewrite this. I'm doing this because this is e to the x and this is e to the 2x. So that's kind of a clue that what we might be able to write this as a quadratic function. So if u is e to the x, if u is e to the x, then e to the 2x would be u squared, right? You square this, you get e to the 2x. So u squared minus 3 times u, right? Instead of e to the x, is u plus 2 equals 0. Okay, great. So this is a quadratic equation. Now, can we factor this? Yes, we can. So we can write u minus 2 times u minus 1 is equal to 0, right? Now, let's bring back, now that we factor this, because our objective is to solve for x, right? So we can now go back to bring back the e to the x to this equation and substitute for u. So e to the x minus 2 times e to the x minus 1 equals 0. So from this one, if e to the x minus 2 is 0, then e to the x must be equal to 2. And so take the natural log of both sides. Natural log because the base here is e. So natural log of e to the x is equal to natural log of 2. Then we have x times natural log of e equals natural log of 2. So we know that natural log of e is just equal to 1. So 1 times x is just x equals natural log of 2. That's one of the solutions. Right? We also have the other factor. So e to the x minus 1 equals to 0, then e to the x equals 1. Once again, let's take the natural log of both sides. Natural log of e to the x is equal to natural log of 1. So this is again this side, just like this, it's equal to x, right? This is equal to x, just like before. So we have x, and then, or over here, just like this. Just similar to this transition from here to x, we have that. X equals natural log of 1, which is 0. I should have actually written down zeros, but x equals 0. Like that. So either this or that would be the solution of our equation here. Okay, either that or that. Okay, so let's do a couple of examples with the limits then. Okay, so we have so we want to find this limit. This is limit of log of 8x minus x to the 4 to base 5 as x approaches 2 from the negative side, from the left. Okay, approaches 2 from the left. So 1.99, 1.9995, and so on. Approaching 2 from the left. Okay, so then as x approaches 2 from the left, all right, so let's see. So as x approaches 2 from the left, then we have, let's see what happens to this quantity. Then approaching 2 from the left. So this approaches 0 from the left, right? 0. So then 8x minus x to the 4, right? Because 8 times 2 is 16 minus 2 to the 4th power, that's minus 16. So, and it gets closer and closer to 0. At 16, it's perfectly 0. But we're saying as x approaches 2 from the left. So this quantity approaches 0. Okay, so then we know that log of 0 or natural log of 0 is undefined. Okay, so how do we say that? How do we say that symbolically? Okay, that it's undefined. Well, we just say that that limit is equal to in negative infinity, actually, because if, let me use the scratch paper for natural log of any number, any value between 0 and 1, it's a negative value. And this is true, sorry, I'm just using this as a scratch paper. So natural log of any value between 0 to 1 is a negative value. The same thing is true for log of any value between 0 and 1. It is, again, a negative value. So in this case, as this quantity is approaching 0, then we're within that interval, right? So all the log values are becoming smaller and smaller negative values. Okay, so they are negative because this value is approaching 0. So anything between 0 and 1 will have a negative log or natural log value. But they are becoming increasingly smaller and smaller and smaller negative values, which means this quantity approaches negative infinity. Therefore, we can say limit of log to base 5 of x minus x to the 4 as x approaches 2 from the left is equal to minus infinity. Okay, minus infinity. Okay, let's do one more example. So we want to calculate the limit of natural log of sine of x as x approaches 0 from the right, from the positive side of the real number line. Okay, so we know what happens at sine of x, right? At sine of x, we know what happens to sine of x at 0. Right, sine of x at 0 is equal to 0. But natural log function at 0 is undefined, right? So this value gets, as this x approaches 0, it gets closer and closer to 0 from the right. And because those values are between 0 and 1, then the natural log would be some negative value that is that is small and gets smaller and smaller and smaller as x gets very, very close to 0 from the right hand side. So we can say that as follows. We can show our line of reasoning as follows, that as x approaches 0 from the right side, and then of course, sine of x also approaches 0 from the right side, right? Not from the negative, but from the sine of x, not natural log of sine of x. So sine of x approaches 0 from the positive side. And then as that happens, then the limit, so the limit of natural log of sine of x. As x approaches 0 from the right, it's going to be getting closer and closer to negative infinity. In other words, the values become increasingly smaller and smaller negative values. So this one will also be negative infinity. Okay, so this will help us apply limits to calculation of, so take the limit of natural log and log functions. Okay, so we've come to the conclusion of another section. I want to thank you for watching this video until the end. For now, have a nice day, and I'll see you again next time.